Thank you for being here at the end of the day. It's been a long day. Let me see. Okay. All right. So this talk will help you maybe rethink and summarize what you learned today and yesterday. And I'll start by saying the obvious. The coverage in the media of generative AI has been up and down and very extensive. In the winter, ChatGPT reached 100 billion users monthly in a very short period of time. And then the media considered this a threat to Google search. But then reporters started talking to ChatGPT and the conversations went off rails. So then the thought was, well, is this a threat to humanity? Are these systems going to become too good for, for what we think of them, and will they just destroy us? In Italy, ChatGPT was temporarily banned because of violations of the GDPR law for privacy and for age verification. But the technology went on, and public APIs for integration were released, and many smaller companies started developing applications. Meta released Llama 2 open source, which was a pretty serious event because it democratized the field quite a bit. And the Screen Actors Guild strike that just finished, I hear, right before that it turned out that Tom Cruise was negotiating with the studios the possibility of using or not using the likeness of actors via AI in the movies without paying the actors. So that's a pretty significant thing. And I could prepare 5 other slides like this. These rapid developments and this intense interest, they create many open questions, such as, can you reliably tell AI outputs from human outputs? I think a lot of high students tried to do this, and even OpenAI released a tool for telling generated text from normal text, and then they took it down. That's really a problem that cannot be solved as far as we know now. Can you ever trust AI outputs, since you cannot really distinguish them from human outputs? That's a big question. And of course, will AI destroy the humanity? But if you're developing products in the short term, there are also questions that you would have after listening to all the talks and going to all the demos. How do we avoid hype? Which frameworks to use? And which applications or application domains can be disrupted by generative AI? So the point of this presentation is kind of simple, that to answer these questions, you have to understand the limitations of the technology and how it is used, and you would look for ways around them. There have been a lot of naysayers for AI, and many of them have been proven wrong. So I'm not saying that there are hard limits. I mean, there are, of course, there's physics and speed of light, but we are not quite there yet. But the way the models are built, and we'll go over this in the next 20 minutes, they lead to some limitations. And if you understand them, this will suggest what to develop, how to go around limitations, and on which pitfalls not to step. Okay, the rest of the talk, I'll review some background and some foundations with an eye on limitations and help you develop intuition. What questions to ask when you look into a new application, and so on. I'll talk specifically about some limitations, and this list is going to be a bit unstructured in the sense that there are a couple of different limitations that are not related. But fundamentally, you would look for ways to circumvent limitations. And the conclusion of this talk is that you want to think of ways to circumvent limitations. Okay? Let me start with this table. Here, I take toy problems, and we can evaluate them. These are prediction problems for what the predictions are based on, what errors you are getting, both error scale and error frequency, and is this monetizable, right? And they start as toy problems, so don't take them too seriously. Can you predict the position of an airplane 5 minutes in the future? You could use preceding data. Airplanes typically fly on straight lines, and when they make turns, that's in the flight plan. So you have a lot of information. The error size is small. You could predict this quite well. The frequency of errors will be small, but monetizing this is probably not a good idea. It's too straightforward. Okay? The next one is very different. Predicting the outcomes of coin tosses for fair coins. If the coin is fair, you have absolutely no data to base the prediction on. And the error size, basically, it doesn't really matter. If you could predict things with some probability of success better than random, you could monetize this, right? You could go to Las Vegas and start winning games, right? But it's just not feasible. So some prediction problems that people require in applications or ask, you just need to be ready to not having enough data to make a prediction. And some things are just random. The next one, multiplication, right? Can you multiply two numbers and predict the result? Well, it's kind of trivial. You can just directly calculate. You don't need data. You don't need to learn from tables of multiplication. And in fact, this doesn't work very well with LLMs and other technologies, right? And so it's a commodity. That's another example of what happens sometimes. You know, some things are just not really great applications for ML, okay? Predicting the stock market for the next day, just up or down. This could have a lot of value, very monetizable, right? And there's a lot of data for this, and there are algorithms, but this field is super adversarial, right? So again, you have to worry about certain things where there are too many companies trying to do the same thing, right? So it becomes not a prediction problem, it's a fight with each other. And the last one is going to be used, you know, on the next few slides, sentence completion. So if I give you the prompt to be or not to be, then, well, you could continue. That is the question. That's Shakespeare. And you have prior data. Getting the correct answer is negotiable here, frequency and magnitude. But if you want to monetize just that, then you have to be really good, right? Because that's competitive and there's a lot of technology, but it's a useful piece of technology, okay? So the next step here is to develop this idea of prediction of continuing the sentences. We have you know, prompts, 2 prompts, and the first one is for the Beatles song, all you need is, does anyone know? Love, yes. And in machine translation, all you need is? Good. So my conclusion is all you need is context. Right? Depending on the context, the prediction will be different. And the context is, the length is measured in tokens, as you know from LLMs. So the colored word pieces there are tokens, and that's from a different Beatles song, not All You Need Is Love. But the vectors that are shifted a little bit, I meant for each colored piece to have a vector. A token can have an embedding as a sequence of numbers, and then you predict the next tokens using deep networks, right? And the reason you use GNNs, there are a couple of different reasons. One is, you know, they're really good at consuming a lot of data and training for prediction. They generalize very well. So in addition to the examples that you give them, they can extrapolate, they can interpolate, and there is no other technology that is so good at this as DNNs. And another thing, they can transform data. There are a lot of AI techniques that just, you know, give you classifiers, right? But DNNs can really transform data. And so that's super useful. However, there are pitfalls. And, you know, this is half background, half limitations. First of all, I'll just say the obvious, the answers to all known questions, or any known question, can be memorized. So if you're evaluating, you know, a ChatGPT or some other bot or some other technology, and you're given it the prompt that other people have probably given before, and you're amazed at how good the answer is, well, that's because they just saw this before. And with big data, with huge data sizes, with large models, memorization by itself gives you a huge boost in performance, right? So question answering, when you go back and forth, is a little harder to spoof or to memorize, but still, don't underestimate the power of big data. So if you take that, and on top of that, perform interpolation, extrapolation, and some generalization, then you get a really powerful technology. But it's still hard to evaluate. Right? So if you majored in organic chemistry, you will talk to ChatGPT and ask questions about organic chemistry. If you majored in Norwegian history, you will ask those questions, and you may get very different results. Okay? And that happens. You could see what people write about evaluating these bots. So now back to this memorization issue. Long contexts and broad scope, they complicate memorization. But with enough money, enough training, enough data, you could cover a lot of stuff that people think about. Okay, and the last point on the slide is randomized answers, right? You could think of always having the right answer, but imagine the situation, you ask a chatbot, tell me the funniest joke, and it will say, well, 2 LLMs walk into a bar, and then you ask the same question again. So if the answer is deterministic, it's not funny, right? And this is a more general point that randomization is important. So these answers are often randomized, which makes it even harder to evaluate. Okay. Let me do another one on background and pros and cons, but all these technologies, machine learning specifically, they're based on learning from data. They don't actually have a specification of correctness. So you give it a lot of examples, it remembers those examples and generalizes, and those who expect 100% correctness, they will be disappointed because you didn't even tell the model what correct means. Because of this, errors are inevitable, and this makes it different from software engineering, where you build components, you put them together, you build large systems where every component works reasonably well. Here, large systems accumulate errors. So if you're building a chain of tools, right, and every tool definitely has errors, right, embeddings, DNNs, a lot of things, these errors multiply exponential. And if you do many rounds, if you iterate, then you take this probability of correctness, say 0.99 or 0.96, which is pretty good. I mean, usually they're lower. And you put this into some power. You see the plots, how the error goes down. So in 100 rounds, you will have more incorrect answers than correct answers. And these errors can be at different levels. They can be, just a missing token or missing word, or they can be very significant. The answer can blame, the wrong person in some dispute, right? So the answer to this in conventional, system design is error correction. You build a large system, and the system needs to correct its errors in some way. And that part is kind of missing in these technologies that we are discussing, right? So I'll show an example how this is done through prompt engineering. But error correction that's an example of how to circumvent limitations of errors, right? And there are different types of error correction. You could plan an answer, that's a forward error correction. You could check the answer. You could recheck the answer with the same model. So we'll get there. Now, let me try to go over this quickly because you know this stuff. There are 2 slides. I'll have more columns on the right. So how are LLMs trained? Just so that we are on the same page here. Think of how children learn language. At first, they learn words and sounds. They repeat words, just what they hear. That's unsupervised. Then you tell your child, this is a ball, and the child repeats, this is a ball. And then the child will answer questions. You teach the child to answer questions. You give them examples how to answer questions. And the answers will still be coming from a child. So you want to adjust. You want to tune these answers, and that's going to be in the columns that remain. But then children start asking questions. Why is this happening, right? Why is the car moving fast? LLMs don't do that yet. So that's another thought to consider, right? But basically, for the training, there is self-supervised learning and huge amounts of data, not great quality, but web and everything else. Then you have supervised learning with smaller amounts of question and answer pairs or prompt and response pairs. And then you tune the answers. So you don't know how to express what's good. You just look at the answers and you rate them. You look at 2 answers, say A is better than B, or B is better than A, and then maybe certainty, 5 degrees of certainty. And then you take these data and put them into reinforcement learning with human feedback, and then the answers are tuned to give you better answers out of several possible answers. And randomization helps here because you can get a lot of different answers. Okay, so I'm skipping a lot of technology, but this is well published and well known. So the next point is, what happens in this tuning, reinforcement learning with human feedback? You want not to just improve the style, but you want the answers to align with what's called human values. This is very different from the old Turing test, where a machine would pretend to be, a college student or, a grandma or a 5th grader. That's interesting, but now we want these chatbots to actually not offend anyone. And 5th graders could make a lot of mistakes that you wouldn't want the chatbot to make. And in fact, pretending to be a person for these systems is not great legally, right? For various reasons, right? So you see these responses as an AI model, I cannot do this, I cannot do that. That would not pass the Turing test. But we don't want it to pass the Turing test. So one way or another, I gave you here 3 bullets, starting with the green bullet from the OpenAI's plan for alignment research. And it's kind of striking. The first bullet is essentially reinforcement learning with human feedback. At least it solves that first bullet. The second bullet realizes that you can't get enough human feedback. The throughput is not good enough, and so on. So they train computers, AI systems, to improve human evaluation. And even that is not enough. And the third bullet is basically everything else. So that's a problem that will not be solved for a long time, if ever, but we can be better and better. Now, can alignment be pursued in the framework of response evaluation? The answer is basically no. First of all, it's not only, well, there are many different aspects why no, but I picked the most important ones. It's not only evaluation, you want to tune, right? And it's not read-only evaluation because societal values need to be negotiated. If you look at how the Congress deliberates, some people change their minds, right? And no company, as far as I can tell, is equipped to do that, right? So that's where we need some larger, expression of what these values are, right? And frankly, many of these slides could be used to give an hour talk each, so I'll skip and speed up. But before we jump to limitations directly, let me just say a few words about prompt engineering. So prompt engineering started as a kind of buzzword and a fad. And of course, your mileage can vary depending on what you do. It's also very system dependent. But it's super powerful for the simple reason that if you don't like the answer, the response you're receiving, and you know the answer, you can just embed the answer in the prompt and you will get your answer, right? So you could improve the results a lot, every time. However, there are two basic kinds of prompt engineering, right? The first one is just to clearly specify the task, point of view, the form, the style, the length of the answer, who is giving you the answer, pretend to be a mathematics professor, pretend to be, I don't know, Michael Jackson. And then you could tune these prompts to a specific model, if you know its weaknesses, what to avoid, and so on. But there is a much more powerful type of prompt engineering. It's called recursive prompt engineering. So what it does is, first, you ask the language model how to improve a given prompt, then ask it to actually follow its own directions, improve it, then ask language model to use the improved prompt, then ask how the answer can be improved, and then ask it to improve the answer. And believe it or not, if you just do this, it's not hard to implement. This improves results on test scores, like college tests and so on, by 20% or so. Right, very powerful. There was even a paper recently where just adding think about this hard or be serious, it improved the results, statistical, right? There is no reason for that, but this happens. Okay, so to itemize current limitations and circumventing them, and I might run out of time, so I'll cover most of them, maybe not all. Let me just name them. So first of all, data and data types for foundational models. So the first column in my table corresponded to foundational models before tuning. And there are really only 5 data types for which this has been successful so far. I'll name them on the next slide. The differences between thinking or reasoning and being able to speak, that's a huge difference that's commonly misunderstood by the public, but known very well to researchers. Then I talked about error correction, and even detecting correctness or checking for correctness is a big deal. In some applications, it's not clear if the result is correct. But if you do pattern matching, at least you could ensure the level of correctness through patterns. Okay? I'll talk about hallucinations, and I'll talk about the need for augmented foundational models for memory, arithmetic, code execution. This is being done, by many of the companies involved, right? And I'll probably skip limitations of alignment models. Okay, so here are the 5 types of data for which foundational models have been trained successfully: natural language, text, code in various languages with sufficient training data, images, photorealistic or not, speech and audio, and video, right? And I put thumbs up where this was clearly a great success. For natural language, you have these issues of alignment and values and being, impolite or disruptive. And for video, it's just hard, technical, and difficult to lift because there is so much data, but these things will improve, clearly. There is no limitation, okay? This is regarding the difference between linguistic skills versus reasoning skills. There are a couple of papers, and there are more, of course, than this, but one simple test for reasoning versus linguistic abilities is to take problems, say in mathematics, that were solved quite successfully by some of these bots and insert words that are irrelevant. we as people, without even being able to solve some number theory problems, will pick those words because they're not relevant. We can reconstruct the problem. But for the bots, this significantly decreased the success rate in those applications. This tells you they're not thinking, they're just continuing, they're just building sentences and formulas. Okay. Now, correctness and pattern matching. I can't emphasize this enough. If you're building an application, you need to know whether the results are sufficiently correct. And if you're building strategy applications, if you're asking, some auto GPT system to trade stocks for you, well, in that case, actually, you're lucky. You have a number at the end of the month, how much money you lost. But in many other cases, if you want to build an administrative assistant for yourself, how do you even know whether they're better than the person would do, right? It's just hard to say. And so the more you know about correctness, the more you can fix, right? So this reinforcement learning with human or any other feedback, if you have correctness feedback, you can actually go back and retrain the model. But if you don't have that, then it's not clear what to do. So basically, another question is how much you can tolerate errors in your application, right? If you need to be correct on average, even in stock trading, if you're correct 75% of the time, that's great. In the legal field, if you're correct 95% of the time, and 5% of the time you make some grave legal mistake, you can be disbarred, right? And just very different levels of correctness required, right? And so one way to gauge the correctness and tune how practical it is to be correct is pattern matching. If your scope is narrow, if you narrow down the field, it's much easier to build patterns and maybe then some generalization. And that's really the way to build applications in the near term instead of building AGI, right, which is risky. Okay? Another way is basically to build an application where you're assisting a human on every step. The human checks the decisions or checks the suggestions, and they can accept and reject. Like coding assistants have been a great success, right? But this is essentially a playbook for checking, whether a particular application is good for Gen AI. Okay, for hallucinations, I'll be really quick. So I had this piece. I asked ChatGPT about myself. That's a thing anyone can do. And until recently, this was a sure way to induce hallucinations. So it would actually give a pretty credible bio. I used to be a professor at the University of Michigan. And it would just make up or say things that I didn't do. It mentioned computer architecture. I worked on integrated circuits, close by, but not that. And now if you ask, who is Igor Markov, or ask about yourself, it will give a different response, most likely correct, but it will be much more bland. It will not have all these details. And that's a good illustration of how to get rid of hallucinations. Well, if you're not sure, then remove the details, or you could put question marks, or you could say, I graduated from University of California, I don't know which campus, right? It said Berkeley, I went to UCLA. Okay, and so one analogy here is blurred images, right? That's a kind of hallucination, but not really. Hallucinations in text, they have all the detail, but the details are wrong, right? And in some cases, of course, hallucinations are useful. Van Gogh, the paintings are like one big hallucination each. Great for art, right? But there is also a playbook how to get rid of, or at least how to try to decrease hallucinations. And ChatGPT improved upon that very clearly. All right, so this is an important point for arithmetic ops. And I'll skip you like computer architecture background and details about numbers, but long story short, it's in practical, these language models cannot multiply large numbers correctly. For various reasons, there is no multiplication algorithm. Someone could build one in, but that would not come from learning, right? And it would not be organically, part of the system, right? But basically, addition can be learned because you can do addition in one pass. It's in the wrong direction. It's like from small digits, from lower digits to higher digits. But multiplication, you cannot do in one pass. That's a theory result. So basically, you need to augment your model. Think about it. If your application requires doing math, an LLM of the current type will not be able to do it because it cannot do math. So you could issue calls to a calculator, but if you do that, you might just as well issue calls to a Python interpreter, right? And so that's a way to augment these models. Okay, and a similar thing goes about memory. There is not much work in memory in these models. They cannot remember many things. Now, Anthropic increased the context to a fairly large size, but still it's not as big as a terabyte of data that you could have in a computer. And again, there are extensions, LangChain and AutoGPT and databases, and just outside there are companies that would give you these databases, but they're not maybe as organically integrated with the language model. So that's something to keep in mind. That's a type of limitation, and maybe there's a way to circumvent it. Okay, so I'll probably skip this. This could be like a philosophy lecture at some point. Yeah, please do take the pictures. But there are some fundamental limitations. Reinforcement learning with human feedback is not going to be the ultimate answer. We understand that. Even there are some mathematical, no matter how well you do it, how many people you employ, there are some purely mathematical reasons, and the mistakes will happen. Just two quick examples, completely different from the errors. LLMs, they actually don't have common sense, right? Common sense and let's say intuitive physics, which is kind of in the same space of immediate reaction, right? Babies learn intuitive physics very quickly, right? They don't bump into walls after a certain age. They know where a ball will fly, right? So they predict these things, and they do this without having foundational models, without having a huge number of data samples, supervised or not, right? And they don't have a lot of reinforcement learning tries because the bandwidth of experimentation is very low. So there are other ways to do this, right? And it would be great to discover them. We just don't know what they are. But in terms of common sense, I have an example on the right. And I used to give these talks, and I had a lot of examples. Every time I would check my slides, I would check the examples, and some of them would be done correctly by the bots. The bots are improving. But this one stayed for some time. I haven't checked it yesterday. So you basically ask, you say, Bill Gates is a Maricopa County supervisor, which is true. There is a Maricopa County supervisor in Arizona named Bill Gates. Does he know much about Microsoft? And it just cannot, ChatGPT just cannot understand that there's another Bill Gates, right? Just impossible. And it admits that maybe, but it just cannot, right? So no common sense. Now, wrapping up, what to expect of generative AI? And there's some quotables here. So I mentioned that there's a lack of human reasoning skills, and it's not clear if there are superior reasoning skills. There are definitely superior linguistic skills. So I would say that Gen AI would not catch with top experts in investigative tasks that require pulling data and being creative and noticing things, but it's faster in routine tasks. And it makes a lot of tasks routine, in particular anything that looks like translation. From language to language, from language to code, from code to language, from language to image, right? It's also great at hand in style. You could ask it to write some text and then say, change the style, speak with, I don't know, a strong French accent, and it will do it, okay? So Steve Pinker, way back, said two things that are very prescient. One is the idea that thought is the same as language is a conventional absurdity. Was true in '94, true now, even truer. And the main lesson of 35 years of AI in '94 research is that the hard problems are easy and easy problems are hard. And we see this with Gen AI, right? Correctness becomes a hard problem. You have so much stuff you can check it. But generating language, which used to be a hard problem, becomes easy. Okay? And there's this great paper, 8 Things to Know About Large Language Models. I think I covered most of that here, one way or another. So conclusions, and I'll be kind of on time. The field is developing very quickly. It brings new opportunities for impact, but it's very structured in the sense that there are pitfalls, there are things you need to understand, there's foundation, there are applications, there are limitations. And these pitfalls, people have already hit, OpenAI hit this pitfall with a detector of text generated by machine learning, right? And there are just many attempts, and take my word, they will not really work very well, except in some applications, and sometimes you can just do better and better. So, for fraud detection, you do want to try this, right? But you will not have a 100% answer. So understanding the limits or limitations is critical to moving ahead, right? One thing is it allays technology fears. Why do you think Llama 2 is released by Facebook? Because we understand, or Meta, because we understand the limitations. It's not as dangerous as some people think, right? And it helps, it levels the playing field, right? But understanding the limits such as arithmetics, memory, verification, allows you to augment LLMs in different ways, right? And build the tool chain around LLMs to build credible applications. Thank you very much. I think we are out of time, but I'll be around after the session.